Hello everyone, welcome to week 9. This is the first lecture of this week. What we'll do today, this week is we'll apply, we'll see how the how force method can be applied to beams, for indeterminate beams and frames. And we have already introduced force method, method of consistent deformation. And then we already have applied method of consistent deformation for trusses. Therefore, the concept of method of consistent deformation is already known to us. What we'll do is we'll just apply that concept in beams and frames this week. Okay, but before that, there is very interesting theorem, which is called the theorem of three moments, or also called three moment equation. That is again the derivation, that is again derived based on the concept of method of consistent deformation, and this three moment equation is very useful for continuous beam and for the beams where the support may undergo settlement. What we do today is we will derive this equation and then see how it can be used to determine the internal forces for continuous beam which are statically indeterminate. Okay. Now, suppose consider a continuous beam. Okay, it's a 4-span. For demonstration, I have taken a 4-span continuous beam, but it is true for any continuous beam, which is subjected to some arbitrary loading. Okay, some external loading, like this. So this is an indeterminate structure. For this structure, what is the degree of static indeterminacy? The static indeterminacy for this problem is 3. We have 2 reactions set here. One is this, and then one reaction upward, By, Cy and Ey. So total 5 reactions and number of equations available 3. So Ns is equal to 2. So it is, so Ns is equal to 3. Ns is equal to 3. Total 6 reactions and 3 equations available. Okay. Now, then suppose since it has 3 static indeterminacy is 3, then we need to, in order to solve this problem, in order to analyze this problem, we need to identify 3 redundant forces, okay, or moments. We need to identify 3 redundants. Okay, identifying redundants means then we identify force or moments, and then in the indeterminate structure we release the associated constraint. And once we release the associated constraint, then the structure becomes determinate. Okay. So after releasing the associated constraint, the structure what we get, that is called primary structure. Okay. Then we need to, as method of consistent deformation we know, demonstrated in the previous week, then we need to analyze the primary structure subjected to the external load, and then primary structure subjected to the redundant force, get the corresponding displacement, apply the compatibility conditions, written in a flexibility format, and then solve it, get the redundant forces. Okay. Now, one possibility in this case is choose this AY. One possibility is choose AY, BY and CY as redundant. Okay. Now, if you do that, then the structure becomes statically determinate structure. But we don't do that, as the equation of 3 moments suggests, that this equation actually gives how the moments are related to each other at different points. So what we do here is we take the moment at A, moment at B and moment at C as redundant. Now, if we take moment at A, B, C are redundant, then what we need to do is we need to release the corresponding constraint. And what is the corresponding constraint for moment is the rotation. So in this, so we need to provide internal hinges at point A, at point B and at point C. So if we do that, then what happens? So this is the primary structure, once again shown, all the reactions as shown here, and then if we insert 3 hinges, one is at A, this one, and this one and this one. If we insert 3 hinges, then what happened? They essentially, then our redundants are, these are internal hinges, then our redundants are MA, MB, MC. Now, so if we take MA, MB, MC as redundant and provide and release the corresponding constraint. Now, once we have introduced hinge at A, means what? The moment at A will be in the primary structure, the moment at A will be 0, and then moment at B will be 0, moment at C will be 0. That is what is the primary structure, right. Now, what happens? Now, this structure is statically determinate structure. Okay. Why statically determinate structure? Just by looking at this, you can say we need 6 equations because there are 6 unknowns. Then 3 is equilibrium conditions, and 3 additional constraints are moment at A is equal to 0, moment at B, and moment at C is equal to 0. And these 6 equations we can solve for the unknown. So, this is a statically determinate structure. Okay. Now, next, so now suppose what happens? Suppose let us derive the expression very general. Suppose consider this span, consider this span, entire span A, B, and C, this part. Okay, and suppose length of AB is L length AB. And then second moment of area is IAB, and Young's modulus of AB is EAB. Similarly, the LBC, IBC and EBC are the length, second moment of area, and Young's modulus of BC. And okay. Now, so there is no restriction that the beam has to be of same beam has to have the same second moment of area, same Young's modulus. So, there is no such restriction when we have this when we have the general expression. Okay. Now, what happens? Consider only this part, the span A, B, C. Okay. Now, if we take only this span ABC, this is the primary structure. For primary structure means if we only consider this part of the part ABC of the entire structure. So, this is the primary structure, and this primary structure is subjected to external load. Okay. Now, due to this external load, suppose the beam deflect like this. Okay. This is the deformed shape of the beam, and then corresponding slope at B is theta BA, and corresponding slope at B due to in segment BC is theta BC. So, theta BA means that slope at B in member AB or in segment AB or in span AB, and when we say that theta BC, it means that slope at B in span BC. Okay. Now, again, so this is the primary structure. If you remember the steps we discussed in method of consistent deformation, the first step is the determination of static indeterminacy. We have already done in this case. We have seen it is NS is equal to 3, and the second step is identification of the choice of the redundant forces. We have chosen MA, MB, and MC as redundant forces, and the step 3 is solve the primary structure subjected to external load, and the step 4 is analyze the primary structure, which are determinate structures anyway. Analyze the primary structure subjected to the redundant force. Okay. Now, this is the primary structure subjected to external load, step 3, and then this is the primary structure subjected to the redundant forces. Redundant forces are moments at A, moments at B, and moments at C. Okay. Now, suppose under the action of these redundant forces, the beam deflect like this, and the slope is denoted by theta bar. So, theta bar BA means again slope at B in segment AB, and that theta bar and this slope is due to the in the primary structure due to the redundant forces. Similarly, theta bar BC is again slope at B in segment BC when the primary structure is subjected to redundant force. Okay. Now, then suppose the bending moment diagram for this is this. You have taken a very arbitrary shape, This is the bending moment diagram for span AB and span BC, and similarly this is the bending moment diagram for the primary structure subject to the redundant force. This is very obvious, because you see, other than moment there is no other loads here. So, at C the moment will be MC, and at B in this case the moment will be MB, and between B and C, since there is no other intermediate load, the variation will be linear. So, MB and MC the variation is linear. Similarly, for AB, at B the moment is MB and at A moment is MA, and the variation is linear. So, this is the bending moment diagram for this part. Okay. Now, so what we will do is we will calculate theta bar, theta BA, theta BC. These are the corresponding displacement, right? This is step 3. This is step 3. If you remember, step 3, and this is step 4 in method of consistent deformation. Okay. Now, step 5 is application of the step 5 is the compatibility condition. Now, compatibility condition means it says that how the associated deformations are compatible to it, how related each other, should be related each other in the actual structure. Now, since our constraints are moment here, redundants are moments here, the associated displacement are rotation. So, what we will do next is we will determine what is theta BA and theta BC, and in the primary structure subjected to external load, then theta bar BA and theta bar BC in the primary structure subjected to the redundant force, and then apply the compatibility condition, which says that how theta BA, theta BC, theta bar BA and theta bar BC should be related to each other in the actual structure. Okay. Now, so let us see how to do that. Now, before that, let us recall the moment area method. We will be using moment area method. What it says that moment area method has two theorem. Okay, and it says that suppose if this is elastic curve, this is elastic curve, this is elastic curve or elastic line, this black line that you can see, this is a deformed shape on a beam. Now, you take any point A and B. Now, draw a tangent at A and draw tangent at B, and the angle between these two tangent is theta AB, and this is the bending moment diagram between A and B. Now, what moment area method says? The moment area method has two theorem. The theorem 1 says that this theta AB is essentially the area of this bending moment diagram. Bending moment diagram means the area of m by I diagram. Okay. And then what theorem 2 says is that if you take B is the actual point in the beam and B dash is the deviation of B or the projection of B on slope drawn at A, then delta AB, delta BA, which is the deviation of B on slope drawn at A, is essentially the moment of this diagram about B. Okay. Okay, this is actually moment. This is theorem 2. This is not theorem 1. Okay, that is moment area method. So we have already discussed moment area method in details. What we will do is we need to find out, as we have seen in the previous. As I said in the previous slide, that we need to find out these theta BA, theta BC, theta bar B and theta bar BC. These angles or these slopes will determine using moment area method. Okay. Now, this is the moment diagram for this case, and this is the moment diagram for this case. So, let us do that. Now, suppose the deviation of point A is A bar, A dash, and this distance is delta AB, and similarly deviation of point C is C dash, and this distance is delta CC, delta CB. This should be B. This should be delta CB, delta CB. Okay. Now, means it is deviation of C on slope drawn at B. Now, similarly, we have delta we have delta AB, delta bar AB here and delta bar CB here. So, so delta AB will be the area of this bending moment diagram from A, moment of this bending moment diagram from A, and delta CB will be moment of this diagram from C. Similarly, delta bar AB will be moment of this diagram from A, and delta C bar will be moment of this diagram from A. And suppose let us first consider the first primary structure subject to the external load. Then this is say x AB, which is the centroid of this, and this is x CB, distance from C of the centroid of this part. And suppose AAB is the area of this diagram and ABC is the area of B. So, area of this diagram. Okay. Now, then moment area method says that delta BA will be moment of this area about point A. So, moment of this area point A will be and divided by EI. So, moment of this area would be MAAB into the centroid, distance of centroid, divided by E and I of segment AB. Now, once we know this distance, and if we assume that this displacement is small, that is what our assumption right from the beginning, then this slope can be written from this displacement as this. Okay. So, this angle is we can write this divided by this length. Okay. So, delta BA divided by LAB. Now, delta BA we have just now found this using moment area method. So, theta BA becomes this. Now, similarly, delta CB will be moment of this about point C divided by EI. Moment of this will be area of this multiplied by the centroidal distance, area of this multiplied by the centroidal distance divided by EI. EI in this case it is EI of BC, and then again assume that this angle is this displacement is very small. We can write theta is equal to delta this distance divided by L, and finally, we have theta BC is equal to this. Okay. So, we have already determined what is theta BA and theta BC. Now, then next we need to determine what is theta bar BA and what is theta bar BC, which are these corresponding slopes in the primary structure due to the redundant forces. Okay. Let us do that. So, we have determined this. Okay. So, this is the bending moment diagram in the primary structure, which is subjected to redundant force. We have just now seen it. Now, in this is bit simpler because in both any segment you take, this bending moment diagram is a trapezoidal. Okay. So, we can determine this the moment of this bending moment diagram very easily. So, theta bar BA will be again moment of this diagram about point A, and if you do that for any trapezium, and this will be the expression, final expression, and divided by EI. Similarly, theta BC will be moment of this diagram about point C divided by EI, and then again it is a trapezium. So, finally, what we get theta bar BC is equal to this. Now, we have obtained what is theta bar BA and what is theta bar BC. Great. So, step 3 and 4 are done. Next step is to apply the compatibility condition. Now, what is compatibility condition in this case? You see, now compatibility condition is compatibility condition will be, you see, suppose you take any continuous beam, take say in this case it is ABC for instance. Suppose this deflect like this, so under the another any action of load, okay, and we draw a slope like this. So, this is AB, right. This is ABC. So, this is the deflected shape and this is the slope drawn. So, what is this angle? This angle will be theta, this angle is theta BA. Okay. And then what is this angle? This angle will be again theta BC. Okay. Or now or you can take a deflected shape like this. Okay, let it be like this. So, theta B and theta BC. Now, what compatibility says, since the slope needs to be continuous at that point, otherwise the governing equation itself is not varies. So, this should be equal to minus of this. The minus because the how the slope is being calculated. Okay. So, this becomes, so theta BA is minus of theta BC, or we can say that theta that is equal to minus of this, that is the compatibility condition, or we can say that this plus this is equal to 0. Now, so in this case also the compatibility condition will be same. If we apply the compatibility condition at B, then it says that theta BA is the, so what is the total rotation at point B? At point B, total rotation is rotation due to in the primary structure due to the external applied load, and rotation due to the redundant forces. This is the total rotation. And similarly, what is the rotation at B in segment BC? This is due to the externally applied load and plus the redundant forces. Okay. And the compatibility condition, just now we showed that the total rotation at B in segment AB should be equal to total rotation at B in segment DC negative of that. Okay. Now, we have already obtained the expression of each, all these expression just now we have obtained, and just substitute those expression in this equation, and if you do that, then our final expression will be this, and this is now we just slightly, if we manipulate it, then this is the expression, and this expression is called, now what this expression tells us. Now, in this expression, you see all these values are known. What is the length of AB, and then length of AB, this value, then this value is known because this is a length and second moment of area, length and second moment of area. These are also known. These are also known. These are also known. These are also known. Only unknown in these equations are MA, MB, and MC. This MA, MB, and MC. Okay. So, and right hand side is known. So, what this equation tells you? This equation tells you how these three moments, at moment at A, moment at B, moment at C, if you take two consecutive span, and how the moments at 2-3 consecutive supports, they are related to each other, and this equation gives you that relation, and therefore, this equation is called 3 moment equation, means how these 3 moments, moment at B, moment at A, moment at B, moment at C are related to each other. Now, if you don't take, now we have obtained this expression because we took span AB and BC. Now, instead of that, if you take span DA and AB, then what this equation will give us? This equation will give us what is so moment at D is MD, moment at MA is MA, and moment at B is MB. So, if we apply 3 moment equation at point A, the compatibility condition at point A, and get the 3 moment equation for span DA and AB, that moment equation will give you how the moment at D, moment at A, and moment at B, they are related to each other. Similarly, if we take span BC and CF, then this gives us how moment at B, moment at C, and moment at E are related to each other. Now, you see this is essentially the method of consistent deformation, and but written in a different form. Now see, in this case, how many equations, how many unknowns we have? We have total 6 unknowns, 2 reactions here and 4 reactions, total 6 unknown, and total 6 unknown, and how many equations available, equilibrium equations available is 3. Okay. Now, we need 3 additional equations, and what are those 3 additional equations? If we forget about 3 moment equation, if we apply the method of consistent deformation, these 3 additional equations will be the compatibility condition at A, compatibility condition at B, compatibility condition at C, right. Now, these 3 moment equations are essentially the compatibility condition at different supports, but written in a different form, in a very general form. Okay. So, you get the 3 moment equation at A, at B, and at C so if you have 3 additional equations, so total 6 equations, you can solve this structure. So it is essentially the method of consistent deformation, and the step 5 where you from step 1 to step 4 they are exactly same. The step 5 when you apply the compatibility equation, this compatibility equation is essentially the 3 moment equation, but it is written in a different form, in a very general form. Okay. Now, so this is 3 moment equation. We are not going to apply this 3 moment equation today, we will do it in the next class. But let us see one more cases. As I said at the beginning that the continuous beam and also the beam where the support support may settle, in that case also we can 3 moment equation gives us a very handy expression. Okay. Suppose again consider the same beam subjected to same external loading. Now, what happens? Suppose support B settles. Now, if support B settles, then what happens? Because suppose it settles and B point B goes to B dash, and this settlement is delta B. Okay. And it may happen, I mean, if you see any structure, sometimes the foundation may settle, okay, and the structure get tilted, and there are many kinds, many practical structures are like this. Now, what happens if the support is settled, then because of the settlement you get the internal forces because of the external agitation, external forces, right. But in addition to the effect of external forces, if the support settlement takes place, then this support settlement will also induce some internal forces in the beam. For instance, you take a beam or any structure which is subject to the external load, right. Now, because that external load will induce some stresses in the structure. Now, in addition to those external load expressed in a distributed or concentrated moment and forces, if the temperature change takes place, okay, if the temperature increase or temperature is decreased, so effect of temperature if you have to consider, then what happens? Then the temperature, in addition to the effect of those external forces, temperature will induce some additional stresses. Okay, so total stresses will be in any structure is the stresses due to the external load plus the stresses due to the temperature variation. Very similar to that. In this case, it is the additional stresses are developed in the beam due to the settlement of this support. So what we will do is we will see then how this effect of support settlement can be taken care of in the expression that we derived just now. Okay. Now, you see, suppose this is the beam, if support settle B, just an animation how the deformed shape may look like. We will consider this problem in the next class and analyze this. Now, you can see this total deformed shape that you can see, that deformed shape is the contribution from the external load plus contribution from the settlement of the support. What we are going to do is we are going to find out that contribution and add to the moment equation that we derived just now. Okay. Now, suppose consider again span ABC. Suppose again it is subjected to the external load. Suppose again let us derive a very general expression where all the supports where we consider the settlement of all the supports A, B, C, but in a structure their values may be 0, but the expression we will derive is a very general. Suppose support A settles by delta A, support B settles by delta B, and support C settles by delta C, and the corresponding position of point A, B, C are A dash, B dash and C dash. Okay. Now, suppose delta B A is equal to delta B minus delta A. So, delta B A essentially is the relative settlement of point B, also settlement of point B relative to A. Similarly, delta B C is the delta B minus delta C, it is settlement of support B relative to support C. Okay, settlement of support C. Now, because of this support settlement, what happens? When the structure is subjected to external load, it deflects, it gets some deflected shape. At every joints, you have some rotation, right? Now, what happens, and because of the settlement of the support settlement will also contribute to those rotation. So, you get, in addition to the rotation due to the external load, you get rotation at the joints due to this settlement of support. And what are those additional rotation? Additional rotations are, you see, if delta BA is the relative displacement or relative settlement of B relative to A, then the rotation takes place at B will be delta BA by LAB. LAB is the length of AB. Okay. And similarly, if delta BC is the settlement of B relative to C, and it will cause rotation, which is very obvious, because if this additional support is, if additional support is, now if we take, if it is LAB, it is LAB, and this is delta BA. So, delta B will cause additional rotation at point B, this additional rotation at that point, and this additional rotation will be this divided by this length. Okay. Now, so this is similarly delta BC. Now, remember, we have used three symbol. This is written, this is expressed as theta hat. Okay. Now, what we have right now is this. Now, this is so now we have we after introducing the redundant forces and associated releases in the structure, what we have is, we have primary structure subjected to external load, and because of this external load, this primary structure undergoes some deformation or rotation at the joints. Then we have the primary structure subjected to the redundant force, and because of the action of redundant forces, the primary structure subjected to undergo some deformation and joints at the rotation of the joints. And then in addition to that, we have support settlement in the primary structure, and then because of this primary structure, because of this support settlement, the primary structure undergoes deformation and rotation at the joint. So, total rotations will be rotations from the rotation from effect of in the primary structure. The total rotation will be the contribution from the external load plus contribution from the redundant force plus contribution from the support settlement. Okay. Now, we have derived, it is the contribution from the primary contribution from the external load, and we have also derived, this is the contribution from the redundant forces, and then this is the contribution from the support settlement. Then we apply the compatibility condition. What is the compatibility condition at B? Compatibility condition, this is the total rotation at point B. In AB, this is the total rotation at point B in BC, and this rotation will be equal to the total rotation will be equal to 0, but this is equal to minus of this. In the previous case, if there is no support settlement, this becomes 0. This part becomes 0. This part becomes 0 if there is no support settlement. Okay, and then the compatibility condition will give you the expression that we just now derived. Okay. Now, if we substitute the values of all these values of theta in this expression, what we get is this. Okay. That you can easily check. Okay. So, in the previous example, this part was not there. This part was not there because delta BA and delta BC were 0 if there is no settlement of support. Okay. Now, so this is the general expression for three moment equation. Okay. So, this is the contribution from, these are the up to this is the contribution from, only the external load, and this is the contribution from the support settlement. Okay. Now, in the general expression, get some special cases. First, you see, in this case we have assumed all are different, length of different segments are different, Young's modulus, then moment of area, those are different, then settlement at different joints are different. So, this is a general expression. From this general expression we have some special cases. The first special case is if you take EI is constant. So, if you take EI constant, then all these EI we can remove. Okay. Then if you have EI constant, then your expression becomes this. Then in addition to that, EI is constant, and then if there is no support settlement, then this part becomes 0, this part becomes 0, and your expression becomes this. This is a very simple expression. Okay. So, any problem if you find that EI is flexural rigidity is constant and there is no support settlement, so you can start with this expression. If you find that EI is constant, but in addition to that there is support settlement, then you can start with this expression. And if you find that EI is not constant, and then the support is also support settlement also takes place, then you can start with this general expression. Okay. Now, we apply these at different joints, get the corresponding equations and solve them to get the unknown redundant forces. In this case, unknown redundant forces are moments. Okay. So, this is 3 moment equation, which is very useful for continuous beam and beam where the support undergoes settlement. What we will do is the main purpose of today's lecture has been to derive this equation. Now, we will see how this equation can be used to find out to internal forces for continuous beam. That we will be doing in the next touch. So, next lecture will be 3 moment equation, some examples. Okay. See you in the next class. Thank you.